This is the last lecture related to lecture number 1, last part of the lecture. So, as I said earlier, there are two possibilities. One is single fracture in the composite material, or you have multiple fractures, layers of multiple fractures. So, these happen as a result of the breaking strain of the individual constituents being less than the other. So let's consider the first case where the breaking strain of the fiber is less than that of the matrix. And most of the time this is the case. Okay? In this case, single fracture will happen if in a constituent equation possibility, if the stress on the fibers times the volume fraction of fibers is greater than the stress on the matrix times the volume fraction of the matrix minus factor called sigma prime matrix times volume fraction of matrix. And since the failure strain of the fiber is considered in this case less than that of matrix. So suppose you had the stress, you can calculate the stress on the matrix required to produce a strain equal to that of the breaking strain of the fibers. So suppose, so that's a, this is a, this may be a slightly complicated way of describing it, but if you read that paper by Aveston, Kelly and Cooper, you will understand this a little bit better. So in this case, you will have single fracture, one single fracture if the matrix is unable to stand the additional strain beyond the fiber failure strain. So most of the time, if the breaking strain of the fiber is less than that of the matrix, you will have multiple fracture in the matrix if the matrix is able to withstand the additional strain beyond the fiber failure strain, which is most often the case, and the failure strain of the matrix is sufficiently large that the fibers are fractured, but the matrix is still holding the whole component together. Now, most of the time you can assume that it is the other way around. So you will have multiple fracture of the matrix, but the failure strain is of the matrix is less than that of the failure strain of the fibers. But assuming that that is not the case, this is the definition or derivation of this single fracture and multiple fracture. So let's reiterate. You will have single fracture if the matrix is unable to withstand the additional strain beyond the fiber strain. That's the case most of the time. I mean that will be the case if the matrix is unable to withstand that additional strain. But you will have multiple strain, multiple fracture if the matrix is able to withstand the additional strain beyond the fiber failure strain. And you can mathematically you can calculate that to be the case also. So if that is the case, you also have to consider what is called the load transfer between the matrix and the fibers, or between the fiber and the matrix. So if the fiber is already failing and it is going to transfer the remaining load onto the matrix. So this is going to be determined by the maximum stress tau which the interface or the matrix can sustain. So The thing to note is that most of the time the fibers have the longer elongation to failure. So in that case, you have the stress on the fibers times the volume fraction greater than the stress on the matrix times the volume fraction of the matrix plus the stress prime on the fibers times the volume fraction of the fibers, where the stress prime fibers is the stress on the fibers at the failure strain of the matrix. I hope it is not too confusing, but that's most often the case. So to reiterate, you have two choices. Either the fibers can break first or the matrix can break first. And most important point to note here is that if you are designing with composites, you are not going to be, just like in the case of the of metals and alloys and things like that, the design with composites is going to be different. So we are interested at the first matrix cracking stress, what is called the euphemistically called the first matrix cracking stress. So beyond that, if your matrix is going to have cracks all over the, if your composite is going to have cracks all over the place, then this material is no good anymore. So you are only going to be interested in the stress below the first matrix cracking stress or below the first point where the non-linearity of this composite starts. So this is, again, to reiterate, it's called the first matrix cracking stress. So this is the point where it is the case. Okay, so that's all you are interested in. When will single fracture happen? Single fracture will happen if the second phase, either the matrix or the fibers, cannot withstand the additional load after the first phase has failed. So it will immediately fail and nothing more can be done about it. You can have some amount of strain, but most of the time this is no good. So you are only interested in this point or this point. So how do you calculate what is the point where you will have a transition from multiple to single fracture of the fibers or from single to multiple fracture of the matrix? So in this case, you have two cases. A is if you have a brittle fiber and a ductile matrix, and B is if you have a ductile fiber and a brittle matrix. So this is probably a little hard to understand. You will have to read the Aveston, Kelly and Cooper paper a couple of times to understand this better. Okay. So as a rule of thumb, polymer composites try to increase a fiber volume fraction to the maximum value possible, which is typically between 55 to 65%. In fact, you have 65%, because what are you trying to do? You want almost all the load to be carried by the fibers. Okay, so that is 55 to 65%. Ceramic composites typically contain 40 to 45 volume percent fiber loading. And the reason is because if you increase it beyond this point, your processing becomes extremely complicated and tough. So you don't increase it beyond 40 to 45% in the case of ceramic composites. But in the case of polymer composites, you want to have as high a fiber volume content as possible. So to reiterate, this is how it is. A whole bunch of equations. I realize it's a little hard for you to get it in the very first attempt, You will have to go over this, and everything in composites is kind of determined or defined by this particular theory. And whatever progress has happened in the case of composites has happened as a result of this ACK theory. And the nice thing is that whatever we determine, it has followed this theory with very little modifications. Okay, so this one is a quick review of that. So as I said to you, I think I sent you these two papers, so please look through that. It will give you a better understanding of the whole process of composites. And this is almost a theory that has been around only for about maybe like 40 to 50 years, unlike in the case of alloys and metals and things like that. So people are still learning more things about this. So I would like you to give me an understanding of this with equations as to about how and why toughening takes place in fiber composites based on whether the fiber is stronger or stiffer than the matrix and vice versa. So I will set up a Dropbox for you. So please submit it as a PDF file. Okay, and I will also be posting the Roy Rice papers on the ceramic toughening theories.